let's start working on those building blocks we're going to use to make our op amp. So I am not going to bore you guys with a lot of derivation today, so we're not going to go through it nearly as meticulously as we did in 335 and 336. I'm hopeful that we will take care of all three of our amplifiers today instead of spending about a week on each. So let's start with the common source amplifier. So our common source amplifier should look something like this. This is our gate, our drain, and our source of our transistor. And we want to actually use it as an amplifier. We're going to have some capacitance Cin here. Potentially some resistance Rn here. And then here is our input voltage signal, Vn, as a function of time. Okay. So we're going to look at this circuit from two perspectives, the first of which is our large signal or DC model, to understand how it behaves, because the bias point that we established greatly affects how it performs as a small signal amplifier, which I'm sure most of you, well, I hope most of you remember, let's put it that way. And this large signal behavior is what's used to calculate some of our small signal parameters. So for our large signal model, or DC model, we are effectively going to employ the superposition technique, which means that we're going to leave all of our DC sources on and turn off all of our AC sources. Because this is a DC circuit, our capacitors are just going to look like an open circuit. And so what we should have is something like this. Let's see, here's our open circuit for our transistor. And then here's our input resistance, R sub N. So what we're going to discuss with this guy is how to determine our gate voltage. So treat all of these voltages that I'm about to talk about, at least all of these single subscript voltages, as nodal voltages. So they're all going to be measured with respect to ground. So we need to figure out what's going on for VG, what's going on for VD, and what's going on here for VS. Additionally, we're going to be interested in our drain current IB. So to calculate VG, what would we do? Let's start there. Any thoughts based on how we understand how a transistor operates? Pardon? VG, the voltage present at the gate. Yeah, just a simple voltage divider circuit here, right? So we know that no current can branch off and flow into the gate because it forms a capacitor, right? So that capacitor, the internal capacitance of the transistor is going to look like an open circuit as well. So just using simple voltage division, we can see that VG is going to be VDD, our supply voltage, multiplied by RB over RA plus RB. Our source voltage here is going to be 0 volts by inspection because we have it directly connected to ground. And from this, we can then say that our gate source voltage, which is what tells us how our transistor operates, is exactly equal to VG. We know that our drain current, ID, will be 1/2 mu n Cox W over L, VGS minus VTH, quantity squared, where I'm making an assumption here. What is that assumption? Okay, so I'm making two assumptions here. You pointed out the one I forgot about. What's the other one? So say that louder. Saturation, absolutely. Assume saturation operation. And channel length modulation effects are negligible to the DC operating point. I'm saying that specifically because we're going to ignore channel length modulation for our bias circuits to kind of give us a fast and loose way to figure out how we need to set this thing up. We are not going to ignore channel length modulation for any of our small signal models because it's going to have a large impact on the small signal performance of our circuits. Okay. So that's why we got to use this particular drain current expression, which is the one for saturation with channel length modulation being ignored. Okay. So now that we know, I have enough information to figure out what our current is based on our bias, then obviously VD, our drain voltage, is going to be simply VDD minus ID times RL. And just to put this back on your radar, this quantity RL can't be excessively large because it will force the device to operate in the saturation region, right? So there is a limit to how large RL can be to keep the device in saturation, right? Where VDS is greater than or equal to VGS minus VTH, which is our saturation conditions, okay? So any question about this large signal analysis? This one's pretty straightforward. Everybody seem reasonably okay with it. All right. So I don't have enough for, let's do the small signal model here. So as I mentioned a little while ago, we're approaching this from a superposition-based analysis method, right? So we know what our large signal operation is going to look like because that's what all those DC parameters tell us. Our small signal operation then is going to be only the effects of our input voltage source being on and all of our other external supplies and things like that being turned off. So VDD is now ground because that's a voltage source. And when we turn off a voltage source, it shorts to 0 volts. So our small signal model is going to look like this. Our input voltage signal Vn of t is now turned on. We have our input resistance here, Rin, and we have some resistance right here that is going to be Ra in parallel with Rb, since VDD now looks like a small signal ground. That's why Ra and Rb are in parallel. And then this is our gate terminal. This is our source. And so here we'll have GM VGS, where here is VGS. And then on this side, we're going to have our resistor R out, which is the channel length modulation resistance, in parallel with our load resistance RL. This is our drain terminal, and this is the pin where we would take our small signal output voltage. Okay. So, any questions about where any of this stuff came from before we start analyzing things? Anything not make sense here? Again, we're working under the constraint that VDD is now looking like a small signal ground. So, I think a rather obvious question might be, where'd the capacitor go? Right? For the capacitor to look like an open circuit at DC makes perfect sense, but why did I not draw it here? Anybody have any thoughts? Or anybody know what assumption I'm making? Right? So the assumption that I'm making is that the excitation frequency of Vn of t is high enough that Cn, excuse me, looks like a short circuit. So we know that the impedance of a capacitor is simply 1 over J omega C from back-end circuits 1. So if we plotted capacitor impedance as a function of frequency, so this will be the magnitude of Z as a function of omega. What it's going to wind up looking like is a curve like this, right? So when our frequencies are very, very low, the impedance of the capacitor is extremely high. And when omega is 0, it's an open circuit. It's got an infinitely large impedance. As our frequency increases, the impedance decreases, and above a certain point, it's effectively 0 or a short circuit. So we are making the assumption that we're operating in that range If we were using this as a design choice, we would need to make sure to choose our capacitor value in such a way that it behaves as an open circuit at our frequency of interest, right? So typically speaking, that input capacitor is going to be a large capacitor, right? But we can tailor how large it needs to be based on our application. All right, so our small signal parameters, GM and R out are critically important as to how this thing operates as an amplifier. Since we are in the saturation region, we know that GM will be square root of 2 mu n C ox W over L times ID. And I just want to be clear here, this is our large signal drain current. So this guy is established by DC analysis. Our resistance R out is 1 over our channel length modulation coefficient multiplied by that same drain current ID. So I'm going to scroll up here. We're going to talk now about how to figure out what our small signal voltage is, VG, our small signal voltage here, VD, our small signal voltage here, VS is, and all that kind of good stuff based on the layout of this guy, because it's those small signal parameters, specifically the VGS, how it relates to VN, how it relates to V out, that tells us how this guy works as an amplifier. So our small signal voltage VG should be what? Roll up here. Exactly right. That's just another voltage divider. Okay. So we're going to have Vn as a function of time multiplied by that resistance Ra in parallel with Rb divided by Rn plus Ra in parallel with Rb. So if we wanted, actually, I take that back. I'll talk about that in just a second. What's our small signal voltage? Yes. Still 0 volts. Our source is still tied to ground in both the large signal model and our small signal model. So that means that our small signal voltage, VGS, is just VG or Vn of T A in parallel with Rb divided by Rn plus Ra in parallel with Rb. All right, now this transistor works by converting that input signal, or well, really it works by converting that voltage VGS to some current at the output, right? Where that current, we can see here, is just GM by VGS. So if we wanted to maximize this circuit's ability to transform that input voltage into an output current, what would we need to do? What choices would we need to make with regarding to the size of Ra and Rb? So if we look at, do it in just this part right here, right? Effectively, what we're trying to do is to make VG and by extension VGS just equal to Vn. Because if we don't, we're scaling it by a factor that's definitely less than 1, right? Which means we're minimizing, we're making our input signal smaller, and then we're amplifying that smaller version of the input signal, which means our overall effect is going to be smaller as well. So how do we make this guy right here look like it's close to 1?
Make RA and RB significantly larger than RN.
Exactly right. So we can say that this is just going to be exactly Vn when RA in parallel with RB is much greater than Rn. That's typically not usually an issue because the internal resistance of our input sources and stuff like that are usually on the order of micro ohms, and we typically bias these guys with kilo ohm size resistors. But we could potentially use some sort of, we could be trying to amplify a signal that has some associated large internal resistance that we would need to compensate for. So I just wanted to bring it to your attention. All right, so we know what VG is, we know what VS is. How do we figure out what VD is? Well, I can see right off the bat that my nodal voltage VD is the exact same thing as my output voltage V out, because they're both measured from that top node at the drain with this source as the ground. Now, how do I determine that voltage?
VGS times the parallel.
You're close. You're super close. We were forgetting something obvious. Well, I think it's obvious. Current's flowing in. If this is the positive polarity terminal and this is the negative polarity terminal, that current's flowing into the negative polarity terminal, so it'll be negative GM VGS times that resistance. Right. So our common source amplifier is always going to act as an inverting amplifier. So it converts a positive input signal to a negative output signal. And this is just me doing a little bit of algebra. And what that will allow me to do is to calculate my voltage gain, where voltage gain is defined to be the ratio of the output voltage with respect to my input voltage. And so that's going to be negative GM R out in parallel with RL multiplied by RA in parallel with RB divided by Rn in series, RA in parallel with RB, which we can say will be approximately negative GM times R out in parallel with RL. So we see here that our overall voltage gain for this system is dependent on a parallel combination of resistances. So what's something else that we need to do to maximize our output, right? When we have two resistors in parallel, they are inherently, that equivalent resistance is smaller than the smallest resistance, right? So having those two guys in parallel makes this amplify signals worse than if we only had one of the resistors, right? So what we're going to have to do is figure out a way, effectively what I'm getting at is as R out approaches infinity, our voltage gain will approach negative GM RL. So we want our output resistance to be as large as possible. Since the output resistance is related to gamma and ID, and we can only change one of those parameters, right? Gamma is fixed. Well, it's not fixed per se, in as much as if we make our transistors wider, or excuse me, have greater or smaller length, we have a little bit of control over that, but it's probably a lot easier to bias this guy in such a way as to make our output resistance as large as possible, which then makes our gain as large as possible. All right, any questions on the common source amplifier? All right. So now let's look at our common drain amplifiers, or also called a source follower. So this guy should look something like this. Here's our resistance RA. This is our gate, our drain, our source. I'm going to bias this guy with an ideal current source for now. This is our voltage VDD. All right. So this is our, I'm going to call it a simplified model of a common drain amplifier. And the reason that I'm calling it a simplified model is because we are assuming that we have access to an ideal current source by which to bias this thing. And we all know that we don't actually have access to that, but it'll make our analysis here a little bit easier. And we'll talk about what happens if we modeled this as a practical current source in a minute, which is going to be much more likely a better model of what we actually have. All right. So we're going to look at this guy from a large signal perspective and then the small signal perspective as well. So our large signal model here should look something like this. Sergio, you okay back there? RA, here's RB. RN. There's VG, V, and VS. And here is our drain current ID. Okay. Again, for all of these, we're going to assume saturation operation because we know that the transconductance is going to be larger in the saturation region, which means we're going to get better amplifiers using them. Okay. So if we were to analyze this guy, let's start with something that I hope is obvious. What's our drain current? Exactly right. Right. So when we bias this guy with a current source, we're forcing the drain current to have some fixed value, which is then going to force our source voltage to be at some point where effectively it causes our source voltage to shift around until the VGS across our transistor is what it needs to be to maintain that source current, right? So it's going to move that source voltage up and down, which in turn translates to a voltage drop across our output resistor when we are looking at our small signal model, okay? What is our gate voltage VG? It's the exact same voltage divider that we had a couple of minutes ago. It's going to be the same thing on the next circuit too. I mean, we do it this way for a reason. All right. So VG is going to be VDD times RB over RA plus RB. In this case, VD is just VDD. And VS is a little bit harder to figure out. Okay. So VS is just VG minus whatever VGS happens to be. We know pretty well what VG is, but we got to figure out how all this VGS stuff works. Well, since we know that our device is operating in the saturation region, VGS is going to turn out to be VTH plus square root of twice ID divided by UN Cox W over L. Where this term right here represents our saturation drain voltage, which is the exact same thing as VGS minus VTH, which we have also heard called our overdrive voltage. They're all the exact same thing. We just talk about it in a multitude of different ways because engineers like to be confusing, I guess. All right. So with that in mind, this becomes VDD RB over RA plus RB minus threshold voltage minus the square root of 2 ID over UN Cox W over L. Okay. Before we move on to our small signal model here, let's talk about what's going to happen if we introduce some resistance here that I'm going to call, let's see, make sure I'm calling it the same thing, RCS, our current source, okay? And we're introducing this additional parameter here because we know that ideal current sources don't exist, right? Any current source that we might apply, which will likely be a transistor-based circuit, will have some effective resistance that we need to take into account for. So if we have this resistor in, everything below this purple line will be dealing with the changes that we need to make. How do you think that we'd go about figuring out? So let's ask this question. Our drain current is no longer going to be exactly IS anymore because there's an alternate path. So the drain current is going to split. It's largely going to be IS, but there is going to be some current that can flow through that resistor RCS that we do need to take into account. So we could say that, oh gosh, I'm going to run out of room on this. ID is equal IS plus whatever our source voltage is, VS, divided by RCS. All right, so that's just applying Kirchhoff's current law at that source node. Current is going to pass from the drain to the source of the transistor. None of it can go to the right to flow through the open circuit, so all of it is going to have to go down. Some portion of that is going to be our current source IS. The rest of it is going to flow through that resistor RCS. All right. Does the presence of this resistor RCS change VG? Not at all. Does it change VD? Also not at all. Does it change VS? You betcha. All right. So from that relationship, we could say that 1/2 UN Cox W over L VGS minus VTH squared is equal to IS plus VS over RCS. As a quick aside here, VGS minus VTH squared would be VGS squared minus twice VGS VTH plus VTH squared. That's just me foiling it out. And since VGS squared is equal to VG minus VS squared, that portion is going to look like VG squared minus twice VG VS plus VS squared. So we get back over here to the left-hand side and start doing a little bit of algebra here. And it looks like I might have screwed up my algebra, but that'll be okay. We'll figure it out. I could say that VGS minus VTH quantity squared is going to be twice over UN Cox W over L multiplied by this quantity IS plus VS over RCS. And from this, I am going to have VG squared minus twice VG VS plus VS squared minus 2 VG minus VS times VTH plus VTH squared is equal to that twice UN, 2 divided by mu n Cox W over L IS plus VS over RCS. And let's see here. I'm going to have VS squared. So that's this part right here. And then I'm going to have, let's call it plus for the sake of argument here. So what I'm trying to do is effectively make this thing look like a quadratic equation so that we could actually solve for what VS is, but we need to know what those coefficients are so that we can apply our 8th grade math quadratic formula here. So bear with me while I figure out the signs because I absolutely made an error in my algebra in my notes here. So I'm going to say that I have a -2 times a negative VS times a VTH. So that's going to look like twice VTH from this part right here. I'm going to have -2 VG from this guy right here. And then I'm going to have a -2 over UN Cox W over L RCS over here. When I move this term to the left-hand side of the equal sign, that's where that negative sign comes from. So that guy is multiplied by this, which is why I have 2 times that with another factor of this, move to the left-hand side where that's coming from. And if I'm not mistaken, that takes care of all of my things that are a coefficient of just VS. And then I'm going to have my constant term, which is going to be VG squared. So that takes care of that guy. That guy's taken care of, that guy's taken care of. Then I'm going to have -2 VG. VTH takes care of this part. Plus VTH squared, which takes care of this guy. And then over here, I'm going to have -2 IS over UN Cox W over L. Crap. Are you doing this? Is equal to 0. And so this is my coefficient B. This is my coefficient C. And I can say then to solve for VS, it will be -B plus the square root of B squared minus 4C all over 2, where I'm specifically saying that A is equal to 1. And I am also saying that I expect my source voltage. Actually, I'm going to be on the safe side and put a minus here. I said plus originally, but I think that the source voltage could technically go negative and still make this guy work and stay in saturation. Effectively, we're going to get 2 solutions to this, one of which will make the transistor operate in saturation and the other of which will not. We would have to use the one that keeps the transistor in saturation to figure out if we're biasing this thing correctly. Okay. So that practical current source there does add quite a bit of kerfuffle to our analysis here. Fortunately for us, it's much less of a pain in the butt when we're looking at our small signal model. Okay. So for our small signal model, so for our small signal model for our source follower, what we will have is something that looks like this. Here's our input resistance Rn. Here is Vn of t. Ra in parallel with Rb. Here's our gate terminal. Here's GM VGS. Here's our out. Our drain terminal is now at ground potential. Our load resistor. So we were making the assumption here that we're operating at a frequency such that all of our capacitors look like short circuits, right? So if we scroll up here real quick, this capacitor looks like a short circuit. We should have a resistance RL connected between the source and ground. What happens to the current source? Open circuit. We turn the current source off by replacing it with an open circuit. Absolutely right. So here, this is where my resistor RL should go, and my output voltage V out is the voltage drop over this resistor RL. Our small signal parameters for my transconductance is going to be the exact same thing, but I'm going to write it down just for the sake of argument. Square root of twice mu n C ox W over L times our large signal drain current ID. And our output resistance in this case will still be 1 over lambda ID. So we can observe a couple of things here. The first of which is that our small signal gate voltage VG is still just going to be Vn multiplied by Ra in parallel with Rb over Rn plus Ra in parallel with Rb, just that simple voltage divider relationship. Our source voltage, Vs, is V out, which means our small signal gate source voltage is Vg minus V out. So if we do ACL at our output node, up here, what we are going to have is this current plus this current plus this current added together equals 0, right? So what that's going to look like is V out divided by RL plus V out divided by R out minus GM times VG minus V out is equal to 0. And we can rearrange this guy and find that V out multiplied by 1 over RL plus 1 over R out plus GM is equal to GMVG, where VG is VN RA in parallel with RB divided by RN plus RA in parallel with RB. So this is another opportunity where we could make VGS, or excuse me, our gate voltage be approximately our input voltage by making RA in parallel with RB much greater than that resistance RN. So from here, we could say that our voltage gain AV is, well, I'll make it work here. GM RA in parallel with RB all over Rn plus RA in parallel with RB divided by GM plus 1 over RL plus 1 over R out, or approximately just GM divided by GM plus 1 over RL plus 1 over RL. So before we talk about maximizing this guy, all that kind of stuff, if I had that resistance due to my practical voltage, or excuse me, practical current source, where would that show up in our small signal model? It would be parallel with that load resistor RL. Exactly right. So we could just drop this guy in here. Here is RCS. And then obviously, everywhere we have RL, we would replace this with RL in parallel with RCS. That is the only changes that would need to be made. Said it was a lot easier to deal with in the small signal model than it was with the large signal model. Okay, so let's talk about this gain. What we saw for our last circuit was that we had a negative gain, meaning that if we applied a positive input signal, we got out a negative input signal, right? So we had inversion. Under certain constraints, it would simply be GM times RL, which or negative GM times RL, which means for a well-chosen load resistor, our gain could be used to attenuate signals or make them smaller, or it could be used to amplify signals or make them larger. It all depends on the value of the transconductance, which is set by our bias point, and then it depends on the value of that load resistor RL. This guy, pretty obvious, is always going to be positive. but it's also always going to be less than 1, right? Because GM will inherently be larger, or GM by itself will inherently be smaller than GM plus other things, okay? So how do we make this gain as close to 1 as possible? How would we maximize this, all right? So we could say that when GM is large, our voltage gain will approach 1. And to make GM be large, we need to understand what we're comparing it with, right? So we need GM to be much larger than 1 over R out, which implies that our transconductance times our output resistance needs to be much greater than 1. This will occur naturally in almost every case. Our other constraint then, so this tells us then that our voltage gain will be practically GM over GM plus 1 over RL. Doing a little bit of algebra, that's going to look like GM multiplied by RL over 1 plus GM RL, which tells us that that quantity GM multiplied by RL also needs to be much greater than 1 in order for us to have a gain of approximately 1. So you may ask yourself, you may not now that you've had me for enough classes and all that kind of crap, but you may ask yourself, why the hell am I harping about an amplifier and trying to make the gain as close to 1 as possible? This is our output buffer for our final design, straight up, right? This is going to be a big part of how we're going to be able to drive off-chip loads, is this exact circuit. Okay, so this is just as much of a fundamental building block as our common source amplifier that we talked about a little while ago, which is going to be our second stage. So effectively what's going to happen, and we're getting there bit by bit, is that we're going to have a differential amplifier, which introduces some gain. And then we're going to chain that to a common source amplifier, which is going to boost our level of gain. But that gain is only going to be good for amplifying on-chip capacitances effectively. The op amps that we use, we don't connect them to well, I mean, they do have on-chip capacitances, but we're interested in being able to drive signals on off-chip components. And to make that happen, we need this unity gain buffer to do its job very, very well. I have some notes here on the common gate amplifier, but I think we're going to wait until the next class meeting because I spent too much time talking. So we're going to knock off here about 10 minutes early. All right, thank you guys. If you have any questions about your tests or anything like that, I'm free for the next 15 minutes or so. Vitaly, you look very confused. Are you aware that your exam has been posted online for about a week at this point and is due not today, but next Friday? Yeah. Yeah, no. Yeah, it's totally due a week from today, but you may have a question since this is the first time I've seen you all week. So, okay, yeah, so I'm not saying it's due today. Do not have a panic attack. It is absolutely not. You still have another week to work on it.